This video is on ionization energy. Ionization energy is the amount of energy in kilojoules per mole required to remove a mole of electrons from a mole of atoms. It is always an endothermic process with a positive delta H, and the reason why is because the nucleus has a nuclear charge that's positive. So in this example we are using aluminum, which has 13 protons in its nucleus and therefore has a nuclear charge of plus 13. To remove the outermost electron from an aluminum atom means you have to break the connection between the positive nucleus and the negatively charged electrons. That is what they term a Coulombic force, and therefore, because it's between charged particles, not as opposed to a gravitational potential energy situation, and therefore it requires a certain amount of energy to remove that electron. Now, you can talk about the successive ionization energies of an atom. What that means is, if I have a mole of atoms, I can remove one electron, or I can then move a second one, or a third one, or a fourth one. And you know from the photoelectron spectroscopy that the electrons that are closer to the nucleus require more energy to be removed. You want to be able to explain that pattern. So the explanation for the increase in successive ionization energies, and I'm showing you the equation, like this is removing the first one, this is removing a second electron, third, and then a fourth. You can see that the values go up: 580, 1815, 2740, and then 11,600. For the first three ionization energies, we are not removing a core electron. We are removing valence electrons. So why does it take more energy to remove the second electron than it does to remove the first one? Well, there's two explanations, both of which are equally valid. One is that when you're removing the first one, you're removing it from a 3p sublevel. That is basically a higher energy level or higher energy sublevel, and therefore it's easier to remove. The second ionization energy, you're now removing a 3s electron, and those are more difficult to remove because that is a lower energy sublevel. The other explanation has to do with the fact that when you're removing a second electron, instead of removing it from a neutral atom, you are now removing it from an ion with a positive charge. And because it's got a positive charge and the charges in the atom are not balanced anymore, it's more difficult to remove a second and third electron. So basically, summing it up, when you're looking at a single atom, the first ionization energy is always the lowest value, the easiest to remove. As you remove successive electrons, it requires more energy because you're now removing it from an ion with a positive charge, and you're usually removing electrons that are of lower energy closer to the nucleus. So the Coulombic force between them and the nucleus is stronger. When you get to the fourth ionization energy for aluminum, you see a big jump in the value. It goes from 2,700 to almost 12,000. That's a lot more than just going from 580 to 1815 to 2740. Why the big jump right here? Because once you remove this electron here, I'm down here, right? You're now going to try to remove one of these electrons. And now you're trying to remove what's called a core electron. If you think about the electron configuration of aluminum, starts as 2-8-3. Once you've removed these three electrons, you're now removing a core electron. And core electrons are more difficult to remove. So you see this huge jump. You can see this pattern from all the atoms. Okay, the successive ionization energies are going to increase. Well, let's look at this page over here. Right. So if you look at, let's say, magnesium, it goes from 735 to 1445 in the magnesium row over here, and then all of a sudden it jumps from 1445 up to 7,730. Why? Because magnesium's electron configuration is 2-8-2. So the first two electrons are relatively easy to remove. It is more difficult to remove the second one because you're removing it from a positive one ion, right? But once you've removed those two electrons, you now see this big jump, right? And sodium is really dramatic. So if you look at sodium, right, sodium's electron configuration is 2-8-1. It takes basically 495 kilojoules to remove a mole of electrons per mole of sodium atoms. But then if you want to remove the next electron, it jumps up to 4,560. So if you see a pattern for an individual atom where they say it's atom X, and they give, let's say, the ionization energies are 200, and then they're 300, and then it's like, 2,200. You can pretty much assume that that guy's got two valence electrons because, yes, it took more energy to remove the second electron, but to remove the third one was this huge, huge jump, meaning after you remove the second electron, you're removing a non-valence electron or a core electron. Now, once you get done with talking about individual atoms, okay, in terms of valence electrons and non-valence electrons and patterns in terms of increasing successive ionization energies, you can look for patterns within the periodic table, particularly within families and within rows. If you're dealing with families, the general pattern is this. As you go down in the column, like so, these are the alkali metals, right? And I've listed all the first ionization energies for all the alkali metals. As I go down the row, you can see the ionization energies generally decrease. Now this is really has to deal with a really important concept called shielding. And shielding basically states that the inner energy levels shield the valence shell. So here's this layer here. Let's say this is lithium, right? So our example is lithium. Lithium has 2 occupied energy levels. This inner energy level right here is going to shield this valence electron from the pull of the nucleus. Okay, it's like it sort of like blocks the nuclear charge, right? So the pull that this feels is less than it would if this wasn't there. Okay, so this basically shields the valence electrons from the pull of the nucleus. Well, as you go down a column, you have more and more shielding. Now, nuclear charge is increasing here, but that's not the important variable here. As you get to larger and larger atoms, and as you go down a column, and we're going to do a radius video as well, which I'm going to post as well today, as you go down in the column, the radius gets larger and larger. So, and if you think about it, once you get down to cesium, cesium has is in row 6. It's got 5 shielding principal energy levels. Okay, shielding the valence electrons from the pull of the nucleus. I'm not going to write out the whole shell configuration for cesium. So as you get to larger atoms within a column, and I'm talking specifically about a column, if you go down any column, ionization energy is going to generally decrease because of increasing shielding. What happens in rows is a little bit more complicated. So let's make sure we're clear. So far what we understand is successive ionization energies increase. It's more difficult to remove core electrons than valence electrons. And as you go down a column, the radii get larger. And because of the shielding and the more energy levels that are not valence electrons, it gets easier to remove the valence electrons. If you talk about a row, however, that's a little bit different. Because as you go across a row, let's say you go from by the way, just so you see the pattern here, these are the noble gases. Notice how as you go down that column, the ionization energy gets successively a lower value. All right, but so, and that's because of the shielding, right? So if I go through, the alkali metals, I see the same pattern. Cesium has the lowest of the alkali metals over here. What I really want to focus on right now is what happens as we go across in a row. Now, essentially, as you go across a row, shielding, okay, doesn't change. See, it's not the number of electrons that's important. It's a number of filled energy levels in the core, or filled sublevels within the core. Okay, and the reality is, as you go in across a row, everything in row 2 has 2 occupied energy levels. Therefore, they all have essentially very similar amounts of shielding. Everything in row 3, right? So if I'm looking at row 3, which starts with sodium and ends with argon, everything here has 3 energy levels, which means they all have pretty much consistent shielding. What does change, however, is the nuclear charge as you go across in the row. And we call this now Z effective, ZF or Z effective. And what that means is, because the shielding remains the same but the nuclear charge is increasing, it becomes more and more difficult to remove electrons as you go across the row. So as you go from lithium to neon, you will note that neon, right, has the highest. Now these graphs, by the way, are for first ionization energy. They're not for second or third, right? So we're just talking about to remove the outermost electron. The electron is easiest to remove from an atom. So has the highest first ionization energy, and lithium has the lowest ionization energy for the first one. Why is that? Because the lithium has an atomic number of +3, whereas neon has an atomic number of +10. And this is the nuclear charge. It's the number of protons in the nucleus. And it's more effective because the shielding by the inner electrons really doesn't change very much. So as a general rule, if you're looking at a periodic table, general patterns you should recognize is, if you go to the left, you're going to have a low ionization energy. If you go down here, you'll have low ionization energy. You should know the reasons. For this, it's because of, as you go to the left, there's a Z effective is smaller. As you go down here, there's more shielding. okay? And therefore, down here in the lower left-hand corner, you're going to find the lowest, okay, ionization energies that you're going to find on the table. And you find the higher ones are over here, okay? And we're going to talk about and relate this to radius in a later thing. So that's a general pattern. Lowest ionization energies are going to be in the lower left-hand corner of the table where the radii are large, where there's lots of shielding, okay, which is like cesium, okay. If you're in a row, it's going to be to the left, because when you're in a row, the one on the left will have the lowest ionization energy because it has the weakest nuclear charge. There are anomalies in the pattern that you need to be aware of, and these will be tested on the AP, okay. So the two anomalies occur in these dips. See the dip here? Boron has a dip, right? And then there's a dip for aluminum, right? And then there's, I'm not going to try to find in this one over here. I think it's probably this one over here, but I'm not sure. But they expect you to understand. So this boron and aluminum, they want you to explain why it's easier to remove the electron. So the pattern is not a straight thing. So it doesn't go like straight up. It goes boom, boom, like that. And so you got these two dips at the bottom. And the dips occur in two very specific families. They occur in group 13, which is the group of boron and aluminum, and they occur in group 16, which is where oxygen and sulfur are located. And they have to do with electron configurations, essentially. And so I'm going to explain each one very briefly. So the explanation for the dip in boron and aluminum is that the S, okay, sublevel, okay, shields the P1 electron. That's pretty much it. So in the boron atom, this 2s sublevel shields the 2p1 electron. That means it's easier to remove. Okay, it means the 2s sublevel sort of blocks the nuclear charge. Okay, so it's the effective nuclear charge is a little bit less because the p1 electron is being shielded by the 2s sublevel. And the 3s sublevel is shielding the 3p1 electron. Therefore, it's easier to remove. For the group 16, it has to do with orbital notation and that whole Hund's rule thing. So if you're filling in oxygen's last sublevel with electrons, 1, 2, 3, 4. This second electron that you put in here, okay, and it would be the same thing for the last sublevel for this atom, right, for solar, 1, 2, 3, 4. This, the repulsion, okay, of the paired up electrons in the px orbital leads to repulsion. So essentially, the second electron in the px orbital is repelled by the first electron that's in there, and because of the repulsion, it's easier to remove. So I'm going to summarize this on the next page, but you don't have to really watch this if you took it all in. So very, very briefly, you should know about successive ionization energies. Make sure you understand that as successive it increases. Make sure you understand valence versus core. Make sure you understand valence electrons are easier and have lower ionization energies, core have more. When you're dealing with columns, make sure you understand that as you go down, because of shielding, the ionization energy decreases, all right? And that's because there are more energy levels as you get to the bottom. Make sure you understand that as you go across in a row, because shielding remains the same while Z effective, okay, increases. Okay, over here is where you're going to have your high ionization energy, right? High ionization. And over here at the bottom, here and here are going to be your low ionization energies. Finally, make sure you can explain the two dips in the pattern, which occur at 13 and occur at 16. And in 13 is because a S sublevel shielding, and for here it's px orbital repulsion. Okay, that's done.